Okay, let's go ahead and get started. I'm going to be doing a review for exam 3 today. Exam 3 will cover chapter 5 and chapter 15, chapter 15 being a loose term for enthalpy. As you have probably seen on the homework, there are some questions about Gibbs free energy. Gibbs free energy will not be on this exam, it will be on the next exam. This exam covers the enthalpy equations we've been working with and chapter 5, which was steady and unsteady flow systems. So I am going to start talking. Okay, so for this exam, we are going to have our Thermo Exam 3 review. Okay, so exam 3 will cover chapters 5 and 15. Chapters 5, I mean actually chapter 5 exactly from the book. Chapter 15, I more mean general enthalpy information, mostly focusing on what we've done in the lab and in class, in the lectures and in class activities. Hold on, let me mute everybody. Why is that not an option? Okay. So for chapter 5, I think there's a really nice summary at the end of chapter 5. End of chapter. Summary for chapter 5. In the 8th edition, it's on page 251. It is the nice blue section that kind of breaks down all the equations that were used in chapter 5. And it's just like a nice kind of collated piece of information. I think it's really helpful and clearly laid out. Some of the main chapters 5 topics that we covered were conservation of mass. Conservation of mass. So dm over dt is equal to mass in over time minus mass out over time. Mass flow rate being density times volumetric flow rate or density times volume, velocity times area. Beefy's having a dream. We also looked at our energy equations, where we have our dE over dt is equal to E in over time minus E out over time, where this term is 0 if steady state. We looked at steady state devices. So when you see a certain device, you can assume that it's operating at steady state. These were nozzles, diffusers, turbines, compressors, mixing chambers, heat exchangers, and pipe and duct flow. On page 227, I think there's a nice breakdown of nomenclature for chapter 5. It is where it goes through like what heat is, what work is, what in means, what out means. I think it's just kind of like a nice definition list if you're confused by chapter 5. I think it's a nice page along with the end of chapter summary. Wow, I wrote nomenclature real bad here. You need to know how to use the property tables. For water, refrigerant R134A, and then some of the ideal gases. For enthalpy, this equation is given in the equation sheet, but you need to know this equation, the change in enthalpy of reaction is equal to the summation of the change in enthalpy of the products minus the summation of the change in enthalpy of reactants. This is not on the equation sheet. You need to know this. You also should know that enthalpy of formations are additive, like we've been doing in the equations where you're going to multiply and reverse them and you can add them up, right? Like that's something you need to know. That's not on the equation sheet. That's just something I think that you need to know. For enthalpy, so this is on equation sheet. That one's not. For enthalpy, focus on lectures, in-class activity / Friday problem solving, rather than the chapter. So I have 2 questions on chapter 5. And I have 2 questions on enthalpy. So kind of chapter 15 plus, plus more, plus what we've gone over for 4 questions total.
Can I ask a quick question?
Yeah.
You were saying not in the equation sheet is the products minus reactants. Did you say anything else after that? Was there something else not in the equation sheet or just that?
So the other thing so the other thing that's not, on the equation sheet is the fact that enthalpy can be additive. So, in the example problems we've been working where you have like 3 equations and you want to find the overall equation for the reaction, that you can add up those enthalpies. There's technically an equation for that, right? The enthalpy of reaction for a given reaction is equal to the summation of the enthalpies of each individual component. But that equation's not on the equation sheet. You just need to know that that's kind of how it works. So I'm going to do an example problem with that. And I think it's something you've already seen. You should already be comfortable with it, but it's just not given to you as an equation.
Thank you.
Yeah. Other questions? Okay, well, so I have 2 example problems that I'm going to work. Before I do that, are there any questions about the exam? Anything you'd like to go over? Keeping in mind the exam will be 11:30 on Friday in Holmes, whatever that classroom is, 134 or something. Any questions? Okay, well, then I will keep going. So I'm going to work problem 550 from the textbook. This is from chapter 5. So as I mentioned, there's one question from chapter 5, one question from chapter, or I'm sorry, two from chapter 5, two from chapter 15, chapter 15 being mostly just referring to enthalpy. So this is question 550 from the back of the book. It is this problem. Helium is to be compressed from 105 kilopascal to 205 and 205 Kelvin to 700 kilopascal and 460 Kelvin. A heat loss of 15 kilojoules per kilogram occurs during the compression. Neglecting kinetic energy changes, determine the power input required for a mass flow rate of 60 kilograms per minute. So helium, or gas, is to be compressed. Helium is to be compressed from 105 kilopascal and 295 Kelvin to 700 kilopascal and 460 Kelvin. A heat loss of 15 kilojoules per kilogram. A heat loss of 15 kilojoules per kilogram occurs during the compression. Occurs during the compression. Neglecting kinetic energy changes. Neglecting kinetic energy changes. Determine the power input required. Determine the power input required for a mass flow rate of 60 kilograms per minute. For a mass flow rate of 60 kilograms per minute. Okay, so this problem is compressing helium gas with a certain mass flow rate associated along with pressure and temperature. So helium is to be compressed. That tells us that we are looking at a compressor. We are in chapter 5, so you should be looking for terms like that. Helium is in a turbine. Helium is in a heat exchanger. Helium is in a diffuser. Helium is being compressed. These are telling you about the device that it's using. As soon as you see diffuser, compressor, turbine, pipe and duct flow, throttle, these are all steady flow devices. So helium is to be compressed tells us that we are working with a compressor. So a compressor had this kind of like fan-like structure. We have some sort of shaft that is going to turn or be turned. That has, for a turbine, it's work coming out. For a compressor, it is work coming in. So we're working with a compressor. We have some sort of flow coming in and flow coming out. So helium is flowing in, it's getting compressed, it's flowing out. The mass flow rate that it is flowing at is 60 kilograms per minute. We know that this is helium. We know that the pressure at, I labeled this as 0.1 and this is 0.2. It's arbitrary. It doesn't matter. Pressure at P1 is 105 kilopascal and 295 Kelvin, 295 Kelvin. The pressure at 0.2 is 700 kilopascal and the temperature is 460 Kelvin. So pressure at 0.2 is 700 kilopascal and T2 is 460 Kelvin.
0.1's where the one that you wrote is 0.1, that's where it's coming out, right?
No, the way that I've drawn this here is it's flowing from 0.1 to 0.2, right? So it's flowing up through this compressor.
Okay.
So the way that I have this written, it's flowing this way. 0.1 should always be like your starting point you're evaluating, and 0.2 should be the ending point that you're evaluating. And so 0.1 is where helium is to be compressed from meaning like from this condition to this condition. So like starting, final, initial, final, starting. But you could have written this is 0.1 and this is 0.2. It doesn't really matter. I was going off the way it was drawn in the book. So they have this compressor where the air is flowing up into it, being compressed, and then releasing out this way. Okay, and the last thing we know is that there's a heat loss occurring from this compression. So we have some sort of Q that is coming out of this compressor at 15 kilojoules per kilogram. So we want to determine the power input required. So we know that power is coming in. We also know that because it's a compressor. So we want to determine this power over time, or this work over time coming in, this power input that's required here. So the first thing that we can do is do our mass balance equation. So our change in mass over our change in time is equal to the mass flow rate in minus the mass flow rate out. This system is not losing any mass. There's no mass changing in time. It's a steady flow system. This mass is zero, mass change over time. So therefore, our mass flow rate in is equal to our mass flow rate out, which is just going to be our mass flow rate, which is 60 kilograms per minute. Next, so this is our mass equation. Then we can do our energy equation, the way we always start these problems, where our change in energy of the system over our change in energy of the system, or dE dt of the system, is equal to energy in over time minus energy out over time. This is a steady flow device, so this is zero, steady flow device. So therefore, energy in over time must equal to energy out over time. And we know that our energy equations are these long equations: heat in plus work in over time plus the summation of incoming mass times our fluid flow term is equal to heat out plus work out plus the summation of the outgoing mass flow rate times our fluid flow term. We know that this heat is outgoing because we're told in the problem statement heat loss of this occurs during compression. So we know we have a Q out, but we don't have a Q in. We're told that we want to find the power output here, or I'm sorry, the power input that's required here. So we know that we're solving for this, but we don't have any output of work. We know that these mass flow rates are equal to one another, so we don't need to label these any specific way like M1 or Mn. We can just leave them as M hat from this part, or like mass flow rate. And we know that there is no, so this is going to reduce into just our enthalpy term, because no kinetic energy or potential energy. We're told to ignore kinetic energy changes, and in a compressor, there is no potential energy. There's no gravity influence here. So both of these fluid flow terms are going to reduce into our enthalpies because there's no kinetic energy or potential energy. So our equation becomes the work that is coming in over time, the power in over time, plus our mass flow rate times our enthalpy at 0.1, our enthalpy incoming, has to equal our heat going out plus our mass flow rate times our enthalpy at 0.2 outgoing. It's not wrong to label this mass flow rate as mass flow rate at 0.1 and this one as mass flow rate at 0.2, but we've already proven here that it doesn't matter. Those are the same. Mass flow rate is the same for the whole system. So you can just leave it as basic mass flow rate. If you had two different mass flow rates, or if you had multiple flow rates coming in, that becomes important. But for these single flow steady systems, it doesn't matter. Okay, so we want to rearrange to isolate this power term because that's what we're solving for. So we have our power in is equal to the mass flow rate, moving this to the other side, of H2 minus H1. I moved it to the other side, factored out the mass, plus our our heat coming out. So this is problem 550 continued. Good job, Fifi. Problem 550 continued, where we have our work in is equal to our mass flow rate, H2 minus H1, plus our heat coming out. Okay. From here, we know that we have helium and we are at a I don't. So this compressor is compressing helium gas consistently to 700 kilopascal. So it's going to be considered to be assumed to be a constant pressure inside the compressor and leaving. So we can convert these enthalpy terms into the CP delta T terms. So this becomes CP times delta T for H2, and then minus CP delta T for H1 plus RQ out. We can factor out the CP, and this just becomes our mass flow rate CP times this temperature at 0.2 minus temperature at 0.1. These are saying the same thing. Plus our Q out. So we have mass flow rate, we have Q out, we have our change in temperature. We need to find our CP. So we can find our CP from table A to A. I would probably just give it to you in the problem statement. But when we go to A2A in the back of the book and we look at helium and we look at the CP for helium, we find that CP is equal to 5.1926 kilojoules kilogram Kelvin for helium. So now we have everything that we need to solve this. Our mass flow rate here is 60 kilograms per second, no, per minute, 60 kilograms per minute. Our CP is 5.1926 kilojoules kilogram Kelvin. Our temperature change is from 460 Kelvin to 295 Kelvin. And our Q out, hold on, I'm gonna leave. Okay, so I know that I wanna get a power unit. And so I'm going to look at what my units are going to be right now. My kilograms will cancel. My kelvins will cancel. I'm going to be left with kilojoules per minute. Kilojoules per minute is not a power unit exactly. It is. It's energy per time, but it's not one that we commonly work with. So I'm actually going to convert these minutes into seconds. So in 1 minute, there is 60 seconds. And therefore, I'm going to have kilojoules per second, which is a kilowatt. And then I'm going to have my Q out, which is 15 kilojoules per kilogram. And I know, I'm trying to figure out the best way to explain this. All right, I don't want to tell you the wrong thing, so I'm trying to double check it before I do what I'm about to do. So when we're looking at this problem, this Q out term, here we're left with units of kilojoules per second, and we're trying to add that with kilojoules per kilogram. So we need to figure out how many kilograms are being treated during this compression process, because in the problem statement, it is labeled that a heat loss of 50 kilojoules per kilogram occurs during the compression process. So we're assuming that what's being compressed over time is resulting in this heat loss of 50 kilojoules per kilogram. So in the solution, we have this, this heat loss of 50 kilojoules per second occurs during the process, but this is just per mass, it's not per time, but we need the heat loss to be in something like per time. So if we consider the same mass flow rate here of 60 kilograms per minute times our 1 minute is 60 seconds, then these units will give us our heat loss in terms of kilojoules per second. So now we're able to add kilojoules per second, assuming that during this compression of these 60 kilograms per minute, we are losing this amount of energy per second. So I won't ask you to do that on the exam. Make this leap where you're going to have to assume that you need to multiply this by your mass flow rate. It will, I'll give you your Q out in terms of per time. But for here, in order to get it per time during this compression unit, we need to assume that this mass flow rate is going to play into the energy loss during that time. I'm not going to make you make that assumption on the exam. But so when we multiply all this math out, we get this to be Wn is equal to 872 kilojoules per second, or 872 kilowatts. So this is the power that is required by this shaft turbine to turn this compressor to compress this helium to this higher pressure and higher temperature. So that's the work that is required here. On the exam, you're either going to have steady state problems or you're going to have very simple unsteady state problems. So there's not going to be any very complicated unsteady state problems. Okay, any questions about chapter 5 problems? Yeah, I always kind of round this. This isn't exactly what it is. I think the exact number was a little bit lower. But I just put in like 5.2, I think. Maybe I even just put in 5. I do it on my iPhone, so it's always rounded. I am not a sig fig person. I am not going to be checking that, especially what my thinking for thermo is. I want you to learn the equations and concepts so you can do well in the FE and you can do well in a job where you need to be doing some MC delta T, some basic property table work. And so typically on the FE exam, typically in a job, rounding is going to be acceptable. So I'm generally absolutely fine with rounding. Okay. Other questions? Okay, then this is going to be a chapter 15 / enthalpy problem.
Would you remind me of the unsteady state devices?
Yes, so the unsteady state devices I listed here. So nozzles, diffusers, turbines, compressors, mixing chambers, heat exchangers, pipe and duct flow. I think I forgot throttling valves. As a hint, I like these devices more than these. I think it's a little too complicated to tell right away pipe and duct flow if it's steady state, because we can also have unsteady state in pipe and duct flow. And sometimes you just have to make an assumption, and I don't want you to make a wrong assumption. I think nozzles, diffusers, turbines, compressors, heat exchangers, and mixing chambers are very clear steady state devices that are easy to draw, they're easy to visualize. So those are the steady state devices. Other questions? Okay. So this problem is going to be about the combustion of xylene. So the combustion of xylene produces a large amount of heat and energy. Determine the change in enthalpy standard of the reaction using table 5.3. given that the change in enthalpy standard of formation of xylene is negative 24.4 kilojoules per mole. So the combustion of xylene C8H10 produces a large amount of heat and energy. Determine the standard change in enthalpy of the reaction using table 5.3 given the delta H of formation standard of xylene is negative 24.4 kilojoules per mole. Sometimes you'll also see it written as negative 24.4 kilojoules per mole of reaction. These are saying the same thing. Oh, golly. Hold on. Okay. So table 5.3 from the book, I'm going to give you on the exam, and it looks like this. So it's the same one that was on your Friday problem solving. This is where we were looking at the combustion of benzene and propane. We also have the enthalpies of formation of other common compounds like ethanol, glucose, water, carbon dioxide, and what's the deal of Ray-Bans? Yeah, I don't know. My husband and I went paddleboarding last weekend, and he dropped his prescription sunglasses. So we were looking around for replacements, and everything you look at online follows you around forever. So yeah, Ray-Ban. And then we are, yeah, my dad just bought prescription Costas that were $700. So that's a lot of money. I don't think we're buying those. Yeah, right. We're looking in like the $100 to $200 range because you can't really get prescription cheaper than like $300 or $400 very easily.
I buy direct. I got prescription with the new active transitions for 154.
Was that through your insurance though?
Nope.
Oh.
Straight out of pocket.
From where?
I buy direct.
Oh, I buy direct is like the place you bought them. Okay. Great. We'll look at them. We'll look there for sure. We are also looking at Warby Parker. We bought some try-ons. Yeah, Warby Parker. Yeah, there you go. The ones he lost were Warby Parker. Okay, but that's a lot about sunglasses. All right, so you're going to be given this table. As you can see on this table, there's no information for xylene. So either you need the information for xylene, or I would give you something that's on this table. Okay, so from this, we would need to know that we are, oops. Okay, I'm going to go back to my whiteboard to help write what I'm going to say so it's not confusing. So we are interested in the combustion of xylene that produces a lot of heat and energy. We know that the combustion of xylene, CH10, is going to interact with oxygen, because that's the definition of combustion, to produce carbon dioxide and water. Water is going to be a liquid, carbon dioxide will be a gas, oxygen will be a gas, and xylene is a liquid. I would probably give you that in the problem statement here as like a liquid. Is it zoomed in a little right now? I don't think so. Oh, you're right. Yeah. There we go. Okay. So I expect you to be able to make this equation, a basic combustion equation, where your fuel reacts with oxygen to produce carbon dioxide and water, along with heat and energy. You don't need to know like the heat and energy exactly, but just know that combustion is the reaction of fuel with oxygen to produce carbon dioxide and water. We have worked on this for like 2 weeks now. You've done several of these equations. I've told you this several times. I expect you to know this. So you should be able to draw this equation from this statement. The combustion of xylene produces a large amount of heat and energy. You're given the equation for xylene. So you can write this equation and then you can balance it. So when we balance this, I always start with the carbon, because I have carbon coming from my fuel into carbon dioxide. I know that's a 1-to-1. So I have 8 carbons here. I want to make sure I have 8 carbons here. Then I go to my hydrogens. I have 10 hydrogens here. I have 2 hydrogens here. I need to multiply this by 5. And finally, I look at my oxygens. So I have 16 oxygens plus 5. So I have 21 oxygens, which means that I'm going to have here, I need 21 oxygens. So in order to give me 21 oxygens, I need to have 21 divided by 2, which is 10.5. Of oxygen. For every 1 mole of xylene, I interact with 10.5 moles of oxygen to produce 8 moles of carbon dioxide and 5 moles of water. I would tell you xylene is a liquid. I would tell you the enthalpy of formation of the xylene liquid and the enthalpy of xylene, which is liquid. Okay. Let me check the exam really quick. Okay. So we know that this is the equation that we're looking for. And we know that this equation is what we're going to be trying to get to. On the exam, I give you, yes, you're only going to be using organic fuel compounds. So it's going to be benzene, ethylene, propane, xylene, toluene, ethylene. I think I already said that. Just organic compounds. So some amount of carbon and some amount of oxygen. Yeah. Those are typically what we use as fuel anyway. In your little lighters, it's always butane. In your grill outside, it's always propane. In a lot of industry, we've used B-tex compounds, benzene, toluene, ethylbenzene, and xylene. Ethylene is a common one. They're really common fuel that we combust anyway. In your gas, it's a mixture of things, but there is always going to be like some organic compounds in there that are combusting. So it's always going to be organic. On the exam, I also am giving you these basic enthalpy of formation equations, even though you could look them up from the table and you could probably come up with them yourself. So we have the first one that's given is the enthalpy of formation of xylene is our xylene, and then 8 carbons as a solid plus 5 hydrogens as a gas. The enthalpy of formation of this, you are given in the problem statement, it corresponds with this equation, is negative 24.4 kilojoules per mole for this equation. The other equation that is given, the second equation that is given is carbon solid reacts with oxygen gas to produce carbon dioxide gas with an enthalpy of formation of negative 393.5 kilojoules per mole. This is also the same as what's given in table 5.3, right? Carbon dioxide, the formation of carbon dioxide is negative 393.5 kilojoules per mole. And then the other equation we're given is about water, which we've worked with carbon dioxide and water equations a lot. So these should be very familiar. So the formation of water, hydrogen gas, oxygen gas react to form water with an enthalpy of formation of negative 285.8. So that equation is given, but you can also, find that in the table. This third equation here is where oxygen gas is reacting with 1/2 of hydrogen gas is interacting with 1/2 of oxygen gas to produce water, liquid water. Golly. With an enthalpy of reaction of negative 285.5 kilojoules per mole.
So we don't solve it the exact way that you're solving it right now. Like, for example, in chemistry, I learned that like you put out the equation on top like you did, and then using moles, we multiply. Instead of writing out each equation for combustion for carbon dioxide and combustion for H2O.
So I'm showing you right now what I'm giving you.
Okay.
So I'm writing given here.
Okay.
These are the generic enthalpy equations for your enthalpy of formation for these products. So however you want to work it is totally fine. I'm just showing you what I would give you for the problem.
Okay, got it.
So this would be written like in the problem statement. So you would have the enthalpy of combustion of xylene, like this problem statement, and then this would be given to you, and you would need to be able to write this equation on your own, and then you need to be able to manipulate these equations to get what you want. Okay, so I'm gonna let you try to work this for a couple of minutes just to get a little more practice on it and try to figure out what the delta H standard of the reaction would be. No, you don't have to get these equations. You just need to know what to do with them, right? I'm giving you these formation equations. On the exam, I gave you these equations. The equation for the enthalpy of carbon dioxide is this. The equation for the equation for the formation of carbon dioxide is given by this equation. The equation for the formation of water is given by this equation. You need to know how to look these up in table 5.3 yourself, but you don't need to come up with these equations. I could make you, because we've worked them enough and they're easy enough, but I'm not going to. Okay, so I'm going to give you like 4 minutes to work on it. It seems like some people already have an answer. I'll give you 4 minutes and then we'll go over it. I'm also going to run and go to the bathroom really fast. So I'll be. I've been drinking a lot of water because I feel like might be getting sick, but then I end up having to go to the bathroom in the middle of class all the time because I can't wait like an hour and 45 minutes. Okay, so it seems like several people have gotten an answer. I won't waste your time that you could be using to study. So I'll go over it. Okay, well, let me keep this up. We have this equation. We know that we want to get to this equation. We have these formation equations here. We want to figure out how to make these get to our overall combustion equation for xylene. So starting with the xylene equation, this one's already balanced because that's how I gave it to you. And it's already kind of in the form that we need it to be because of it being balanced. So therefore, we can leave this equation alone, just keep this standard enthalpy here. For the carbon solid, we want to use this to figure out how to get rid of our carbon dioxide. This is the enthalpy of formation of carbon dioxide equation. We know that we want 8 carbon dioxide, so I'm going to multiply this whole equation by 8, including this formation term here, which gives me negative 3,148 kilojoules, because this is 8 moles, so the moles cancel. And then I have my carbon dioxide that's taken care of from this initial xylene equation. I know that my xylene is good, and I have my carbon dioxide here. Then for my final water equation, I know that I want 5 waters here. I'm going to multiply this whole equation by 5, which gives me 5 of my water. I'm going to multiply this by 5 moles. And this gives me negative 1,427.5 kilojoules. This equation I'm going to keep as it is, but it's going to be multiplied by 1 mole, which means it's just negative 24.4 kilojoules. When I look at this equation, I have 8, 8, 8, 5, 5 over 2, which is 2.5, and 5. So my 8 carbons will cancel. My 5 hydrogens will cancel. And then my xylene will be left the same. So 1 mole of xylene plus 8 plus 2.5, 10.5 moles of oxygen goes to 8 moles of carbon dioxide plus 5 moles of H2O. This is the equation that I want, so that's great. I did my manipulations correctly. And then I'm going to add up all of these, which, as many of you said, gives me negative 4,500 and I think I got negative 5,599.9 kilojoules, which is just a little bit higher than what some other people got. I'm not sure where that error is coming from, but it should be 24.4 plus 3,148 plus 1,427.5 based on my iPhone math to give me this delta H standard of the reaction. So any questions about that?
Isn't it products minus reactants?
Not for this way of working it, right? This is you're summing up all of your enthalpies of formation to get your overall enthalpy of reaction.
Okay. So then, like, when would you be doing products minus reactants?
So the products minus reactants, let me go to our class on Canvas, modules. I hope I posted.
Now you're asked to rework the
Oh, that's me talking. So if you remember on Friday, we had some problem solving in class where we were looking at doing this exact same method where you're looking at the enthalpies of formation and you're canceling them to get your overall enthalpy of reaction for the given reaction that you're interested in. That was the first 2 problems that we did. And then the last problem that we did was where we had the combustion of benzene. I believe the exact problem statement was, let me pull it up. So the enthalpy of combustion of these, calculate the enthalpy of combustion of carbon dioxide to CO2, calculate the enthalpy for this reaction given these enthalpies of formation. Those we just worked the same way that we did before. If we did the standard enthalpy change of the combustion of 1 mole of benzene to carbon dioxide and water, then compare the quantity of heat produced by the combustion of benzene and propane. So this is the one where we worked the products minus reactants. Noah, when you worked products minus reactants, you got almost the exact same answer for that last question, right?
Yeah, it was only off by like 48 or something.
Okay, it should be a little closer than that. I'm not sure where that issue came from.
Because it was the negative 24.4. So instead of adding the negative, I subtracted the negative. So wouldn't it be times 2 difference?
Okay.
the 24.4. So instead of adding, I subtracted it, so it'd be difference of 48.8 or something like that. I mean, it's pretty close though.
Yeah. So you should have 5 times water, but water is going to be, yeah, okay, 5 times water and then 8 times carbon dioxide minus 10 times oxygen, which is 0, minus 1 of the ethyl benzene, which is negative 24.4. So it it shouldn't be 48 off, it should be like 24 off. Oh,
Well,
48 'cause times 2. Oh, yeah.
Yeah. I guess I'm just confused as to why here we're just adding them all instead of products minus reactants.
So let me think of a good way to explain this. Well, but when we do products minus reactants, we're still looking for the entire reaction. I don't want to say the wrong thing and right before the exam. So, and then have everybody do something wrong. So I'm trying to be very careful about like what I'm saying. If you work the problem products minus reactants like this, I don't have any issue with that. It is clear on the exam which way you need to be working it. If you are given equations like these, you need to work it this way. If you are not given equations like these, you are able to do products minus reactants. Yeah, so it's pretty obvious like which way you're expected to use it because you don't have enough information if you try to do it one way and not the other. That's like the simplest thing that I want to say that doesn't like mess anybody up. But for this combustion problem that I just worked, I think that if you did it products minus reactants, like I wouldn't take off points. Like that's an okay to work way to work that problem. I'll make it very clear on the exam. I'll even add like a sentence that's like, work this by doing products minus reactants or work this by manipulating the equations. And then I'll follow up about like what case specific situations. Just because I feel like that's the safest answer right now. Okay. Other questions?
Are you going to post the solutions for the homework before the exam?
I already did.
Okay.
Yes. Those should be open. What's confusing me is you should get the same answer either way. So I might have made an issue in the example problem, but you should get the same number either way. That's kind of why I'm like a little confused. But you can work the problem either way. and you should get the same answer. So I wouldn't take off points if you worked it one way or the other, but it's going to be obvious which way will be easier to work the problem, if that makes sense.
I mean, the only way I could see that if there was an error in the example is maybe the 24.4 is supposed to be positive.
Yeah, so I'm pretty sure this is the enthalpy of formation, which means that this reaction should be written the other way around.
Okay, yeah, that makes sense.
Which would make this then positive the way that I've written it, or negative if you switch the arrow, and then that would give you the exact same answer if you did it products minus reactants. Because then you'd have to reverse it. But yeah, so at the end of the day, you can work the problem either way. That's not a problem. Even if the answer is like a little bit different, even if I make some sort of mistake, like it should always work that way. Okay, other questions? No, delta G will not be on this exam. It is on the homework, which is due on Friday, but it's not on this exam. That's going to be on the next exam. I haven't finished going over everything about delta G. So I put a little on this homework just so you can have some exposure to it, but it's not going to be on this exam. Okay, other questions? Okay, well then class on Friday will be the exam at 11:30 in Holmes on the first floor. Bring your calculator, a pencil, and nothing else. No Apple Watches allowed, no anything weird. Just, come like normal, and I will see you all on Friday morning.
Have a good day. Thank you.
Have a good one.